This is the second example of steps for solving instrumentation parts per million questions. The example I'm going to use is question 30B from page 35 of the 2013 CheckPoints in Chemistry, Unit 3 and 4. The first step in any of these questions is to plot the calibration graph using standards. Again, you always have concentration as your x-axis and absorbance as your y-axis. But in this question, the calibration graph is given to you, so you don't need to do it. The second step is to find the unknown concentration by using our absorbance that's given and then reading that off the calibration graph. And in this case, our absorbance of 0.70 would be plotted on the graph to read 35 milligrams per litre of permanganate ions. Step 3 is to calculate the mass of our unknown in our original 1.00 litre volumetric flask. Now in the question, you'll find that 25 mils of that 1 litre flask was taken there. The 25 mils of the original solution will have exactly the same concentration as the 1 litre volumetric flask. That 25 mils was then diluted to 100 mils and placed in another volumetric flask. So when we do the calculations there, the original 1 litre solution will have a concentration of 100 divided by 25, which is our dilution factor, times the 35, which equals 140 milligrams per litre. We can work out the number of moles of permanganate then by dividing the mass this time in grams, which is 0.140 divided by the molar mass of permanganate, which is 118.9, and that gives us a number of moles of 0.00118 moles. Since our number of moles of manganese equals the number of moles of permanganate, because there's one manganese atom in a permanganate ion, that concentration remains the same. So that number of moles remains the same. We can then work out the mass of manganese by multiplying the 0.00118 by the molar mass or atomic mass of manganese, which is 54.9, to give us 0.0646 grams or 64.6 milligrams. The final step here then is to use this mass and the original mass to calculate the concentration in the units required, which in this case happens to be percentage weight per weight. So we've got 0.0646 grams in 13.936 grams original sample. So therefore, to get that in grams per 100 grams, we get the 0.0646 divided by 13.936 times 100, and we end up with 0.463% weight per weight, which could be then converted to 0.46% weight per weight using the correct number of significant figures. Okay, give others a go and see how you go. Repeat this and replay it if you need to go over it more times.